Hello geometry students, and welcome to the lesson for 6.1. Can be found on these pages. We've got some new vocabulary here, talking about polygons today and what is a polygon and what's special about a polygon, and then some special things that might be true about polygons as well as we continue through this lesson. And as always, make sure you're using those extra examples in the book to check out some more things if you need some extra help with the examples that we cover here. Alright, let's get started though. And let's see what we have for basic rules for polygons. What makes a polygon? What is a polygon? So some basic things we have for polygons. One thing that you have to have with a polygon is that you have to have all straight sides. So you have to have all segments, in other words. So I'll write that just as all straight sides. The sides are the segments. And so in other words, you have no curves. No curves are allowed in these shapes. Second thing that's got to be true if you're going to have a polygon, the segments must actually connect. So the sides, I should say, instead of segments, but the sides are just segments, but the sides must connect. The third thing is that you cannot have intersecting sides, so the sides cannot intersect. You can't cross over each other. And then a fourth thing that I can think of here is that you can't, or you have to have at least 3 segments. So you must, or at least 3 sides. You must have at least 3 sides. So a polygon, just a shape, but this shape, something that has to be true about this shape, it has to have all straight sides. The sides have to connect. The sides can't intersect. And you have to have at least 3 sides. If you want to see more with this, let's make a little note here off to the side that there's more on the top of page 322 in your books. So if you want to see more of a technical definition of what a polygon is, you can check it out there. But if you understand these 4 things, I think you're going to understand what we're going to do next here with example 1. So I'm going to draw some shapes here, and you're going to try to tell me through the internet, through YouTube, I guess, you're going to try to tell me which of these are actually polygons. So which of these are polygons, or YouTube, or wherever you're watching this video. Let's see what we have here. So let's draw something like this. I'm actually going to get out my drawing tools, more precise ones, so that you can tell whether sides are straight or not. So let's go with something like this. I did not lift my pen. It's doing that again, huh? Let's see. Wow. Let's try that one more time. Come on, you can do it. It did it again, but pretend that just keeps going straight there. Alright, and there we go. So that's one shape. I'm just going to draw all the shapes in first, and let's have you do the same thing here. So split it up into kind of 6 separate parts, like I have here. There's another one. Alright, let's say we have something like this for this one. And just leaving some room off to the side to write some things in here if I need to. Let's go with just something like this for that one. That's it. And I'm going to draw, I've got this fancy little tool here. Sorry, you're going to have to draw something like that. Freehand sketch, but thank you, tool, for making that easier for me there. Alright, and I don't know why that's in there, but let's see if that goes away. Yes, it does. Alright, so we have something like this. So which ones of these, if any, are actually polygons? So let's look at our rules and see what we have. So with this one, do we have all straight sides? Yeah, these are all straight sides. Remember this, my pen lifted here, but that's just supposed to be one straight side there, one segment. Do the sides connect? No, the sides don't connect here. So we've got a little problem here. This is not a polygon because the sides don't connect. So this one I would say no. And if you had to give a reason, you could say the sides of the segments don't connect. So the sides don't connect. How about this one? Do you have any curves? Nope. The sides connect? Yes. Do they intersect? I think I should be a little more clear on this. What do I mean by the sides can't intersect? I think I should say more like the sides can't overlap. So let's change this word. This is not a technical definition again, but I think this is the way we really understand it best. So the sides cannot overlap. We want them to intersect. We want them to have that vertex in common where they come together. But do these overlap? No, the sides don't overlap. They intersect right there and there, but they don't overlap. I see one down here that does overlap. See if you can figure out which one that is. And do you have at least 3 sides? Yes. So all the rules hold for this one. So I would say yes on that one. How about this one? Isn't that just like a circle, or just maybe it's not a circle, maybe it's just a curved shape or an ellipse of some sort, but either way you have curved sides, you have curved parts. So do you have all straight sides? No on this one. That one doesn't even hold. That step 1 works out there. So you have no curves are allowed here. So that's why this one doesn't work. This one, do you have at least 3 sides? No, you just have 1 side here. So even though there's no overlapping stuff, there's no sides to actually connect, this one, no, you have to have at least 3 sides. So this one you only have 1 side. It's not 3 or more sides. Okay, how about this one, this star shape? Is this a polygon? Do you have all straight sides? Yep. Sides that connect? Do they overlap? No, they just connect right at their vertices. Vertices, plural for vertex. And do you have at least 3 sides? Yeah, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sides actually. So this one holds true. This one's a yes. Is it okay that these kind of cave in? That's alright. So it doesn't matter that it kind of caves in, the angles cave in a bit, you could say. So this one's a yes. You've got all 4 of these things holding true. This one though, I said there's one that have kind of overlapping sides. This overlaps with this one right here. So this one I would say no. You have overlapping sides. So no overlapping. It's not really a technical way to define that, but do you see where see what I'm talking about here, where this right here overlaps with this segment right here. So no overlapping sides. They're supposed to intersect, but they're only supposed to intersect right at the endpoints, and that's not what's going on here. Okay, so let's check out some special names for polygons. You're going to have to learn some special names of certain types of polygons. You've learned a lot of these before though, so it's not going to be a lot of new stuff. This should hopefully be mostly review. So let's put the number of sides in a column over here, and then let's put the special name of the polygon right here to match up with it. So if you have 3 sides in a polygon, a 3-sided polygon is just called a triangle. 3-sided shape, 3-sided polygon is called a triangle. 4-sided, see if you can guess it before I write it down, starts with a Q. You say quadrilateral, you got it. A 5-sided polygon is called a pentagon. Very famous government building that we have in the US here. 6-sided building, or a 6-sided polygon I should say, is called a hexagon. If you think of bees and their hives, you have a lot of hexagon structures in there. A 7-sided one, this one's a little more obscure for most people, but a heptagon. I'm a big fan of the Olympics. They have the heptathlon for the women's events. They do 7 events over the course of 2 days. That's kind of how I remember that one, but heptagon is what we have here. 8, you've seen stop signs before. Octagon for 8-sided shape. 9 and non kind of sound the same, so that's how I remember that one. 9 goes with nonagon. And then 10, I think of a decade, I think of a decathlon, which is 10 events. In the Olympics for the men, they do 10 events over the course of 2 days, a decagon. And then if you have 12, we also need to know that one. This one is called a dodecagon. I don't have a clever way to memorize that one, but just remember that the do in front of it adds an extra 2. Maybe that's a way you could remember that. Decagon is 10, and then 2 more letters gives you 12 for that. And then if you have n sides, we just call it an n-gon. And so let me make a little note down here to kind of clarify that a little bit more. What is an n-gon? In general, not if general, but in general, any n-sided, so it could be like 22-sided, could be 86-sided, whatever the number of sides is, any n-sided polygon is an n-gon. And for example, I said 22 earlier, a 22-sided polygon is, we don't have, there actually are these really obscure special names. These are the only ones you have to memorize though, but for the sake of our class, we're going to call it a 22-gon. In class, my students, I will kind of share just for fun those really obscure special names, and I've got a little list that you can refer to if you really wanted to give a 22-gon the special name that it has, but we're just going to say it's a 22-gon. It's got 22 sides. Alright, let's move on to something like this. So in your vocabulary, if you looked at that, you saw you had convex and concave, or non-convex, another name for that. So convex polygons and concave polygons. Just going to draw in a couple examples here for that. So a convex polygon, I'll get my drawing tools out here, draw some examples of that. I'm just going to draw a triangle. That's a convex polygon. A quadrilateral that looks something like this, that would be a convex polygon. And you might be asking yourself, why are these convex polygons, Mr. Wagner? I don't really know why they are yet. And if you're asking yourself that, that's good. It means you're thinking as you're watching this. That's always a good thing. But what's the difference between these and the ones I'm about to draw? So this is going to be a concave polygon. You might notice why that's concave instead of convex. How about something like this? That's concave. And how about something like this? What makes all these ones concave instead of convex? Well, there's at least one part here. This part here kind of caves in. These two parts kind of cave in. This part kind of caves in. Over here, that's not going on. There's a more technical way to describe it. Basically, that technical way is if you connect any two endpoints within the interior of the shape, and it goes outside of the shape, outside of the polygon at some point, then it's concave like this is. So if I connected this point to this point, there would be part of that segment outside of the shape. If you can do that with any segment, like here I could do it here to here, you'd have part of it outside, and here to here, part of it outside. If you can do that with any segment, you have a concave polygon. But if you can't do that at all, like here, any segment I draw in here is going to be totally contained within the interior of that shape. So what makes these concave, though, in more layman's terms, you might say? So let's write this down off to the side. You have at least, I think this is a part, or this is the way most of us will remember it best. You have at least one part that kind of caves in with concave polygons. Okay, so let's write that off to the side. And if you want to see more about this, you can refer to page 323. So let's write that off to the side here to see page 323 for more. Okay, and then down here, I want to just write down a few more, I think, pretty important things for this lesson. we haven't talked about equiangular within the context of polygons. Equiangular polygons, equilateral polygons. We have talked about equiangular and equilateral triangles before, but really not much different at all. So equilateral and equiangular polygons, you have all congruent angles, just like we had all congruent angles in an equiangular triangle, all congruent angles in an equilateral polygon. You may have guessed it already. It's not that their laterals are equal, I guess they are in a sense, but their sides, that's what lateral refers to, the sides. All the sides are congruent, so all congruent sides. And regular polygons, just like a regular triangle, was both equilateral, equiangular, regular polygons. They are both equiangular and equilateral. So all congruent angles and all congruent sides when you say something is a regular polygon. All right, and one other thing that I think is really important that we write down here. But before we do that, let's write down one other thing over here. I want you to at least read example 3 on page 323. We're not going to do an example together here in the notes with that because I think it's pretty straightforward. If you just read it, you should be able to understand that. But check out examples there of equiangular, angular, equilateral, and regular polygons, and it should be good to go with that. But one last thing before we do a final example is to write this down. If you look at theorem 6.1, we had a theorem earlier, the triangle sum theorem, that talked about the interior angles in a triangle adding up to 180, and so now we have the interior angles in a quadrilateral, and they always add up to the same measurement. Pretty cool that that works out all the time. In a quadrilateral, any quadrilateral you pick, the sum of the measures of the interior angles is, and I'm going to leave this blank for a moment, we'll put theorem 6.1 over here. I want to actually discover this with you. So off to the side here, just draw a quadrilateral. It can be any old quadrilateral. I'm going to draw mine like this. I'd probably recommend you do a similar looking shape to mine. Alright, and then get out a different color. At this point I want to see a different color for this part. Let's connect that with a diagonal. We're going to put segment in there to there. Make that just a little bit better there. Okay, and let's think this through now. So one triangle we know from before, that's 180 degrees right here. Let's draw that in. And then another triangle, that's still going to be 180 degrees. So if you add those two things together, still doing this in your different color here, 180 plus 180, this is going to work for any quadrilateral. It's always going to be 360 degrees. So I want you to draw that off to the side, something like that, and then we can write that over here. So it is 360 degrees. And really, really important that you get that down. So any quadrilateral you draw, you can always split it up into two triangles. Therefore, it's 360 no matter what the quadrilateral looks like. All right, so let's do one final example where we use this, put that into practice with drawing here. All right, so we've got a shape here. I want to put a Q, a U, an A, and a D right there. And would you look at that, a quad just showed up. A quad is kind of a informal name for a four-wheeled, you might call it, I don't know what you'd call it, I guess. It's not really a motorcycle. Motorcycle has two wheels, but quads, they have these things with three wheels. But this used to be pretty popular back in Michigan where I came from. Especially a lot of people would ride quads around in the woods and have fun doing that. And if you're into dirt bikes and quads, you might have ridden one of these before. They're pretty fun to ride around on. But let's draw in some other angle measures here. That's going to be 76 degrees. We're going to say that angle A is 2x degrees. We're going to say D is 110 degrees, and Q is going to be x degrees. Alright, and our goal in this problem is going to be to find the measure of angle Q and find the measure of angle A. So basically we need to solve for x to do that, and then once we know x, we can plug stuff back in and figure that out. So remember what we just said back here. This is theorem 6.1. Why don't we even circle this? This is really important. So we gotta know this, that any quadrilateral that's going to add up to 360, the interior measures. So based on that, it's pretty easy to set up an equation, I think. So by theorem 6.1, we can say that the measure of Q plus U plus A plus D, that's going to be 360. So we can just say x plus 76 plus 2x plus 110 equals 360 degrees. From there, now it's an algebra problem. So let's combine like terms. We have x plus 2x on this side becomes 3x. 76 plus 110, that's going to be 186. And then from there, you can subtract your 186 from both sides. And that's going to leave you with 3x equals 174. And then if you divide both sides by 3, that gives you what x equals. And 174 divided by 3, I worked that out earlier, and I got x equals 58. Okay, so this is not our final answer, but very important to get our final answer. If we get q, or what is q, we just plug 58 back in, it's going to be 58, because that's q is the same thing as x. So we can say, so the measure of angle q, why don't I circle this, pretty important. Measure of angle Q is 58 degrees. That's a final answer. I'll box that in. And then we also have the measure of angle A. That's going to equal 2 times 58, which is 116 degrees. So the measure of angle A, that goes in right there. That came from right there. Measure of angle A is 116 degrees. Okay, and so hopefully you found that helpful, and let me know if you have questions in class, and let's really rock these problems out and do really well. And please again let me know if you have any questions in class. Thanks.